2.7 VSEPR and bond hybridization. VSEPR or VESPR refers to valence shell electron pair repulsion theory. Molecular geometries are shapes of molecules. Pause the video and read through the learning objectives. So what do you already know? Do you know the shapes of these molecules? Pause the video and answer the questions. The answers to number 3 are shown above. Okay, so let's talk a little bit more about molecular structure and the VSEPR model. The valence shell electron pair repulsion, or VSEPR theory, predicts the geometries, the shapes of molecules and polyatomic ions. The shape or geometry of the molecule is determined by the number of electron domains, pairs of electrons, on the central atom. Electron domains can be lone pairs of electrons or bonds. The central atom of a molecule can have a single, double, or a triple bond, and those are counted as one electron domain. Electron domains are areas of electron density or charge clouds that minimize electron repulsion by positioning themselves as far apart as possible. Okay, so electron domains are really just pairs of electrons. They're going to be in bonds, or they're going to be lone pairs. Okay, and you look at the central atom and you count the number of electrons from that. And electron domains, they arrange themselves as far away as possible from each other. So that means if you have any pairs of electrons, either as bonds or lone pairs, they're always going to spread themselves apart. How many electron domains are on the central atom? Pause the video and work it out. Okay, there are 4 electron domains on the first molecule on water, and that's made up of 2 bonds and 2 lone pairs of electrons. You would do that by working out the Lewis structure as you've seen below. And on the second molecule, there are 4 electron domains, 4 bonds with no lone pairs of electrons. And as you can see, you're looking at the central carbon atom, okay, not the electrons on the chlorine. You're looking at the central carbon atom, and that's the one that has 4 electron domains or 4 pairs of electrons. Okay, so I'm going to go through what these shapes should look like. So the molecular geometry with 2, 3, 4, 5 and 6 electron domains. Okay, and this is when all the electron domains are in bonds. They're not lone pairs. Okay, so this is when all the electrons are in bonds. So if you have 2 electron domains, you get a linear shape with an angle of 180 degrees. And an example, and the bond angle is between the bonds. Okay, so you notice that it's linear, it's straight, and it's 180 degrees. And there's an example, carbon dioxide. And remember, the double bonds are counted as 1 electron domain. So there are 2 electron domains on carbon dioxide which push themselves apart as far as possible. So 3, 4, 5 and 6 electron domains. So if you've got 3, you have trigonal planar shape with a bond angle of 120. You know, you've got 3 bonds in a triangular shape, and if you think about it, you can divide that circular triangular shape into 3 and get 120 bond angle. Tetrahedral, all the bond angles are 1 and 9.5. In a trigonal pyramidal, you've got 2 kinds of bond angles, 120 and 90. So if you look at it, you've got a trigonal planar in the middle, and you've got a bond pointing up and a bond pointing down. The bond pointing up is perpendicular to the trigonal planar, so that's got a bond angle of 90. Okay, and then there's a bond pointing down, also at a right angle to the trigonal planar. And then the 120 refers to the 3 bonds in the trigonal planar. And if you split a circle into 3, you're going to have a bond angle of 120. And then the last one is an octahedral with 6 electron domains, and you've got like a square planar or a square flat shape in the middle. You've got a bond pointing up and a bond pointing down, and all bond angles are 90 degrees. Okay, even in the square planar bit and in the top. And then you've got some examples of molecules that have those shapes. Okay, and remember, these molecules, PCl5, SF6, are expanded octets. Okay, so you've got more than 8 electrons in the outer shell, so they break the octet rule, or they are expanded octets. The other things, 2, 3 and 4, they also break the octet rule. So 2 and 3 break the octet rule, but 4 doesn't. 4 is for molecules that have an octet. Okay, so how do you determine the molecular geometry? You draw the Lewis structures, you count the number of electron domains on the central atom, and then you draw the molecular geometry, and then you label the bond angles and name the shapes. So I want you to pause the video and I want you to try the following, right? So when you've done that, you can also either make those molecules up or go to the PhET animation link. Okay, you can Google PhET animation and molecular shapes and you'll find this. Click on real molecules, okay, and then you can go in, find the particular one you want to do. So for example, you might want to look at water or another molecule like PCl5. You want to see the electron geometry, the molecular geometry, and I'll talk about those a bit later, and you want to show the bond angles. Okay, so the electron geometry is how many pairs of electrons there are, and you'll notice that the bond angle, when you've got a bond perpendicular to the trigonal planar, it's 90, but then in the middle, I'll just try and turn this around, you've got a trigonal planar and there are 120 bond angles in between that flat triangle in the middle. Okay, so the electron domain geometry is how many electron pairs you have. Pause the video and see if you can do these. Okay, so the answers are, so for SiH4 and CCl, those are both tetrahedral structures because they've got 4 electron domains, 109.5. BCl3 is trigonal planar, PCl5 is trigonal bipyramidal, and SF6 is octahedral. Okay, Lewis structures, again, we're going to look at BeBr2, 180. Carbon dioxide also has the same shape. And then SO3 and NO3 minus and CO3 minus, all of those are all trigonal planar with a bond angle of 120. Remember, double bonds double bonds are counted as one electron domain. Okay, lone pairs. How do lone pairs affect the molecular geometry? Well, lone pairs of electrons are the most compact, and they're more compact than bonding electrons, so they repel more. This leads to smaller bond angles. One lone pair reduces bond angles by 2 to 3 degrees. So what I mean by that is if you see a lone pair, right, and it's not in a bond, it will make the existing bonds smaller by 2 to 3 degrees. So you'd need to know what the bonds would be if they were bond angles would be if they were all bonds, but and then you just subtract 2 to 3 for every lone pair. So let's have a look at how this affects 4 electron domain shapes. So if you have just 4 electron domains and all the electrons are in bonds, they're bonding electrons, then you get a tetrahedral shape. But if you have one lone pair, then you get this triangular shape. Now the lone pairs themselves are not counted in the shape, but they affect the shape, okay, by squeezing the bonds closer together. Okay, so that lone pair at the top will be squeezing those bonds closer together by 2 to 3 degrees, and the last one, water, okay, is going to have 2 lone pairs. Now tetrahedral, we already know a little bit about the fact that it's made up of 4 electron domains. Okay, so the electron domain geometry for all of those is tetrahedral because that's based on the number of electrons that you have in the central atom. But the final shape, called the molecular geometry, is different. Okay, so make this clear. Electron domain geometry is tetrahedral for all of them because there are 4 electron domains. But the shape is different. Okay, so you've got tetrahedral for the first one, trigonal pyramidal for the second, and bent for the third. Okay, and you've got examples of some molecules with those shapes. Okay, so if I said to you how many bonding domains and non-bonding domains does each of these molecules have, well, you can tell me that the tetrahedral has 4 electron domains and they're all bonding domains. The middle one has 4 electron domains, but it has 3 bonding and 1 non-bonding. And then the last one has 2 bonding and 2 non-bonding. Even though it has 4 electron domains, it's not a tetrahedral unless all the electrons are in bonds. It's considered bent. Okay, and then the bond angles. What happens to the bond angles? Well, the one in the middle one, the bond angles are 107 because the bonds have been squeezed together by that lone pair pointing up. So the bond's gone from 109.5 to 107. Can you guess what the bond angle would be between the two red circles in H2O? Can you pause the video and guess? It's 104 degrees, okay, because each lone pair decreases or squeezes the bonds closer together, creating smaller bond angles by at least, 2 to 3 for each lone pair. Okay, that's gone down by about 5.5. Okay, so that's how you do it. So you can make these molecular model kits using the Mollymods. So you can make these molecules, using the molecular Mollymod kits, or you can go to the PhET simulation and work and have a look at them from there. Okay, so there, for example, is water, and you'll notice the bond angle, if you let it settle, it's about 105.5, around 105, okay, and it's because the lone pairs push the bonds together. Okay, right. So we've gone through this slide already. So just to remind you that one lone pair reduces the bond angles by 2 to 3 degrees for every lone pair that's present. Okay, let's look at 5 electron domains with lone pairs of electrons. Okay, so remember, there are 2 things here. You talk about electron domain geometry. That's going to be the same for all of them, right? They're all trigonal bipyramidal. But if you start introducing lone pairs, the molecular geometry becomes different. So if you look at the 3 underneath, so the top one is a trigonal bipyramidal. The seesaw and the T-shaped and the linear, you have 1 lone pair each time. Now notice that the lone pair is in the middle where the trigonal planar would be each time. So in the seesaw, it's in the middle, and if you think about it, those lone pairs want to be as far apart from each other as possible. Okay, and the trigonal planar, those bond angles are 120, so they're as far apart from each other as possible. So the lone pairs are likely to go in that triangular bit, so they can be as far away from each other. Okay, so you need to remember the names. Seesaw, it looks like a seesaw if you put it on its side. T-shaped, okay, if it's got 2 lone pairs, and linear if it's got 3 lone pairs. So how many bonding domains and non-bonding domains does each molecule have? Okay, so for the seesaw, it's got 1 non-bonding pair and 4 bonding pairs. T-shaped, 3 bonding and 2 non-bonding, and linear, it's got 2 bonding and 3 non-bonding. Okay, and some examples of molecules with those particular shapes are shown on the right. Remember the trigonal, they're all trigonal bipyramidal for their electron domain geometry, but their molecular geometry, which is their final shape, is different. Okay, what are the bond angles? Well, the bond angles are 120 and 90 in the trigonal bipyramidal, right, as already covered. And then for the others, the seesaw bond angles are 120 and 90. As you can see in the diagram, but although some sources, the lone pair tends to push those bond angles closer together, making them less than 120 and less than 90. For the T-shaped, the bond angle is 90, and for the linear, the bond angle is 180. Have a go at making these molecules. Now let's look at 6 electron domains with lone pairs. So all of these molecules have an electron domain geometry which is octahedral because they all have 6 electron domains. Okay, but they have different molecular geometries because of the number of bonding domains and non-bonding domains that differ. So an octahedral complex has 6 bonding pairs. The square pyramidal has 5 bonding pairs and 1 non-bonding, and a square planar has 2 non-bonding pairs and 4 bonding. Now notice that the lone pairs are in different positions. They're pointing upwards or downwards, and that's because lone pairs need to be as far away from each other as possible. And so by having them pointing up and down on the square planar, what that means then is that the electrons pairs are 180 degrees away from each other, as far away as possible. So then if we look at some examples of molecules with those particular shapes, all right, the bond angles on those are all 90, okay, except for the middle one, which has less than 90 because the lone pair is pushing more than a bonding pair.